right. As David mentioned, I'm here to talk about a hybrid system. What I'm actually talking about is a development of a sequence of systems, actually. The work I'll be talking about today actually started development back at Queen's University and has developed into a couple of other systems over the course of my work at the University of Dundee and now the University of Glasgow, and partially as part of the Sonopil project. So what I sort of want to walk you through is this development of a system that has proven to be very adaptable over time to multiple applications and how we've managed to make that work for the different uses we needed it for. Before I get into the system itself, I just want to give a quick introduction to the Sonopil project itself, which funded most of the research I'll be talking about today. Sonopil project is a capsule ultrasound endoscopy project. We're working on a swallowable endoscopic ultrasound pill, which would hopefully be able to, that's not ghosts. All right, that would be able to image the inner lining of the gastrointestinal tract as seen here using high frequency imaging in the 30 to 40 megahertz range. I'm not pushing any buttons, I swear. Okay, seriously? Sorry about this. Maybe we'll just use pictures. All right, as part of the Sonopil project, it must be on auto. Is it auto advancing? Okay. Okay, I think we're good now. Sorry about that. All right, as part of the Sonopil project, we are developing custom electronics to derive the ultrasound arrays inside the systems using custom ASICs and FPGAs. And one of the things we wanted to be able to do was develop a robust, adaptable set of tests. And so we were looking at a set of test bench electronics that would allow us to test not just prototype high-frequency transducer arrays, but also the ASIC electronics as we developed them, and any potential quantitative analysis tools or other imaging modalities we may want to test. So to be able to do all of these things in one system, or potentially a suite of systems, we needed both broad bandwidth of imaging frequencies, as well as some custom electronics and comparison electronics with adjustable voltage and frequency. Based on all this, we came up with a set of specifications for what we wanted in a transmit system. We wanted to be able to drive frequencies anywhere from 20 to 50 megahertz. We wanted to have a variable output amplitude, up to 100 volts peak to peak, but we also wanted to be able to drop the voltage if we wanted to test things like PMUTs or other lower output voltage devices. We also needed to be able to drive capacitive loads. As many of you are aware, transducers are inherently quite capacitive, and we start looking at PMUTs and other micro machines transducers. These can get up into the tens of nanofarads. We also wanted to have some beamforming in the system, depending on application, which if you're looking at high frequency applications with focal points in the millimeters, we're looking at picosecond tuning for arrays. And we wanted it to be adaptable, unlike PowerPoint. So before we started in on, I don't know what my next slide was. Before we started the actual development of the system, we did want to review what was available on the commercial marketplace, because there's no point in putting in both time and money into a custom system if there was something available off the shelf that was both cheap and readily adaptable to our application. When we ended up looking at the what was available out there, we came up with a few different options. There are a few single chip solutions out on the market that do work in the frequency ranges we're talking about. There's some from Supertex, now Microchip, as well as Texas Instruments. However, some of these Texas Instruments parts have require up to 10 power supplies, I believe, and require FPGA triggering, amongst other things, whereas the Supertex parts top out at, I think, about 35 megahertz. I'm trying to memorize my slides here. And so didn't have the frequency range that we were really looking for. In terms of commercial systems, there are a few actually out there now. It's much better now than it was even 10 years ago. Verisonics, Diagnostic Sonars, S-Sharp have all started to come out with systems. However, these are very large, monolithic, multi-channel systems, and let's be honest, a lot of them are very expensive. Whereas we were hoping for something that was desktop-based and a little cheaper. So when we first started this, I'm on up a slide or two. Keep going. So when I initially started to develop this project, actually back during my PhD, when many of these systems weren't actually available. Back a couple. Ooh, I may actually have control now. Anyway, as I was just saying, a few different systems. In terms of what we actually use in the lab right now, we also have the JSR pulsar receiver, which has the frequency range you'd want. However, it's only dual channel and is impulse-based, so you don't actually have that frequency control. You're just driving the frequency, you're just hitting it with the system with a monopolar impulse and hoping you get the frequency out that you want. So based on all that, we decided it was best to go with a much simpler custom solution. The solution we went with was based on a core amplifier, the right slide, design, two-stage amplifier based on a high-rise time, high gain bandwidth op-amp system with a simple CMOS output. Those are ZTEX MOSFETs that we use to drive. They can handle up to 100 volts peak to peak and have sub 5 nanosecond rise fall times. You can see the initial test board over on the right. Next. Okay. And in conjunction with that, as we mentioned, we want some beamforming control. So to get beamforming control without adding complexity to the system, I actually used these pulse width modulation chips from Maxim. These are DS1023s, and the 25 series gives you 0.25 picosecond adjust, and you can use them both for delay as well as pulse shaping, and you can just output pulses down to 5 nanoseconds in width. So the initial chip is used to generate the initial transmit pulse, and then goes through both a coarse delay stage as well as fine delay stages that allows you to adjust both your beamforming delay for each channel as well as your positive and your negative going pulse duty cycle. This gave me a lot of control over each individual pulse, and as you can see, I went with a single channel board design. I did test boards that had multiple channels per individual board, but I found both that this increased the noise in the system, which is always a concern with a transmit pulsar. It also meant that if during testing one of my channels had an issue, I had to take the whole board out and replace it. Whereas with the single channel solution, not only does that reduce my noise considerably, it also means that I can put in and replace each channel individually without having to touch the main board or the adjacent channels. All right. So you can see the final system here. This is a 12-channel beamformer. I believe there's 8 channels active at that point. You see the main power and trigger motherboard, and this is the system operating at 50 megahertz and 90 volts peak to peak. You see there's a slight duty cycle mismatch. We found that the PMOS was a little bit slower than the NMOS part of the circuit. However, once you drop the frequency down to 20 megahertz and still at 80 volts peak to peak, you get excellent 50% duty cycle. Next, thank you. That system worked very well for basic pulse wave driving. However, when we started to adapt it to the Sonapil project in particular, we also wanted the ability to drive continuous wave or longer pulse chains, which the pulse width modulator chips made it a bit more difficult to do. So we simplified the circuit and broke it down into a circuit that would actually work in continuous wave mode. So you notice we've got the same op-amp and MOSFET capability, but now it's a single op-amp that can be driven with a sinusoid or other mode. This also gives us the ability to control the input wave into the circuit. The new boards are here. These are about 1.5 inches by 2.5 inches, 2.5, and also work on a mother-daughter board configuration. You can see the output from this system. This is the final system. Box is about the size of a bread box, And the main motherboard configuration can drive enough current to handle at least 6 boards. We've tested it with 4 boards, but simulations show it should be able to handle far more than that and should be easily expandable. And you can see it operating 30 megahertz full amplitude. We get a little bit of loss amplitude at 50 megahertz. We still get very good pulse definition, single pulse. And then this is a 20 pulse burst, 1 megahertz, 30 megahertz. The one limitation we found with this system was heating. Because the output MOSFETs are so small, we actually can't put big enough heat sinks on them to get all the heat out. However, we were still able to operate at 50% power duty cycle, so 20 cycles on, 20 cycles off at the 30 megahertz, and that's at, I believe, 40 volts peak to peak. So we were very satisfied with that performance as well. Thank you. Finally, getting back to the commercial solutions, we have in the lab an FI Toolbox system, seen here from Diagnostic Sonar. It's a very good pulsar receiver system. However, the transmit module can only work up to 24 megahertz, as tested in the lab. However, we've partnered with Diagnostic Sonar to attempt to adapt the system I previously presented to expand the frequency range of the toolbox. Because the FI Toolbox is a modular system, we're able to take the existing configuration, back one, give up, existing configuration and insert it into the signal chain. So this is sort of the existing signal chain here, and then here's the amplifier that we're inserting into the chain. You can see we've only produced initial test boards. We're seeing some voltage loss at the 50 megahertz, or it's fully functional at about 30, and we've seen in the past that these sort of lab-built boards do have reduction in frequency performance. So we're very hopeful that this adaptation will work and we'll be able to bring the FI Toolbox transmit abilities up to 50 megahertz based on previous performance of this system. So now, I'd like to conclude. I've got the right slide now. I've presented a highly adaptable modular system. The base amplifier system has proven to be very robust over time in 3 different systems now. And because of the simplicity of the system, if we discover newer, faster MOSFETs or op-amps, it can easily be swapped into the system to further expand the voltage and the frequency range of the system at a very low cost. So I strongly suspect we'll be using something very similar for a great deal of time to come. And I'd like to thank you very much.